Redox reactions and electrochemistry. That's going to be our lesson today. So what's a redox reaction? A redox reaction is a reaction that involves electron transfer. Okay, so redox comes from reduction and oxidation. So you can think of a redox reaction as consisting of two half reactions, one involving a gain of electrons, that's called reduction. Okay, that might seem counterintuitive. Okay, students tend to get confused a lot about that because reduction and then you have gain. Why is that called gain? A reduction? Because you're gaining. Think of it as gaining negatives. When you add a negative, you lose, sort of, right? So reduction is a gain of electrons. Oxidation is a loss of electron. A good way to remember this is a few mnemonic devices, memory aids that you can use for this. One most commonly used one is oil rig. Okay, that means oxidation is a loss of electron, reduction is a gain of electron. Okay, or you can say oxidation involves loss, reduction involves gain. Or one of my favorites, I like this one better. Loss of electron is oxidation, gain of electrons is reduction. Leo the lion says, girl. Okay. All right, so classify the following half reactions as reduction or oxidation. Let's take a look at this one. You have a sodium, okay, atom in a solid. So that's a collection of atoms. And then you get ions in solution and each separated from the electrons. Would that be considered reduction or oxidation? Is it A, reduction, or is it B, oxidation? This first one. Remember, what does a symbolic representation like this mean? What you have on the left is what you have before. What you have on the right is what you have after, right? So is that reduction or oxidation? This is what you have before and what you have after. So that means that is a loss of electron. Okay, what you have before has now separated from its electron. So when you see electron on the right-hand side, this is what's called a half reaction. Okay, when you see electron on the right-hand side, that is oxidation. Okay, correct answer here is oxidation. How about the second one? Is that A, oxidation, or B, reduction? I mean A reduction, B oxidation. Sorry, same choices. Is it A reduction or B oxidation? Need one more click. Okay. And that is reduction. Very good. So reduction, electrons on the left. Okay. In the oxidation half reaction, electrons on the right. Okay. So how can we recognize a reaction, a redox reaction? If I gave you a reaction and I tell you, is this a redox reaction or not? Then you say, does it involve electron transfer or not? So how can you tell? Uh, some simple reactions are fairly, some redox reactions are simple enough to be easily recognized. If you have a reaction that involves an elemental substance, as either a reactant or a product, you can pretty much tell that that's a redox reaction. Okay, but you have to keep in mind that not all redox reactions will involve an elemental form of the substance. Okay, so this is a sufficient condition for you to say it's a redox reaction. Okay, but it's not necessary to have an elemental substance involved. Okay, so in general, for you to be able to tell if a reaction is a redox reaction, you have to look at what's called the oxidation state or oxidation number of the elements involved in the reaction. If there's a change in oxidation number, then you say you have a redox reaction. Let's illustrate that first with a few examples. Let's look at some simple redox reactions. If you have a combination of two elements to form a compound, like sodium and chlorine gives you sodium chloride, Okay, you have elemental substances involved. That's a redox reaction. Let's understand why this one is this particular one is a redox reaction. What do we know about sodium and sodium chloride? When sodium is found in a compound, what do we know about it from Chem 105? It's always found in nature to have a charge of +1 if it's part of a compound, right? So sodium, the element, would be a collection of neutral atoms. So what happened here is your sodium atom got oxidized to sodium ion. You see, it got oxidized. That means it lost electron, right? So what happened here is your sodium ended up being sodium ions, and so that means it must have lost, each sodium atom must have lost an electron. So similarly, you can say the chlorine molecule must have been reduced, okay, because your chlorine in your NaCl is actually chloride ions. Okay, you know that from your earlier lessons and earlier courses. So this is a redox reaction. If you have a displacement reaction, you have one element displacing another in a compound, that's also a redox reaction. So what's the element in this? Look at this one right here. Your sodium displaces a hydrogen from water. Okay, so you produce another element here. So if you have an elemental substance as one of your reactant, you have an elemental substance as one of your products, you can tell that you're dealing with a redox reaction. Okay, so that's displacement. What about combustion reactions? And combustion reactions involve reaction with O2, which is an elemental substance. So right away, if you see a combustion reaction, then you know that that's a redox reaction. So magnesium, for example, if you were to burn it in oxygen, you get magnesium oxide. You remember the definition of combustion reaction? It's a reaction that involves O2, and the products are the oxides of the elements in whatever it is you're burning. So the oxide of magnesium is magnesium oxide. Note that this reaction can also be classified as a combination reaction. Okay? Methane, your natural gas, you burn it in oxygen, you get carbon dioxide and water. You get the oxide of carbon. You're burning methane, which is made up of carbon and hydrogen. You get the oxide of carbon, which is carbon dioxide, and you get the oxide of hydrogen, which is water. Okay? That is also a redox reaction. So, given that, which of the following chemical reactions is not a redox reaction? Based on what we just talked about. Start the poll. First thing I look for is what? An elemental substance, right? If you see an elemental substance, you know it's a redox reaction. Process of elimination leaves one possible answer for this question. Let's see. Okay. This has an elemental substance, so that's a redox reaction, right? And you can tell that's a combination of two elements to form a compound. That's the example I just gave, right? Or that's also a combustion reaction if you're burning the magnesium. How about this one? That's a decomposition reaction. That's also redox because you have elemental substances involved. So you have one reactant giving you two or more products. That's, if you recall, that's what you would call a decomposition. Not all decomposition reactions are redox, but if it gives you elements as the products, as one of your products, an elemental substance as one of your products, then you know it's redox. You see elements here. Okay. How about the third one? What kind of reaction is that? You have an element displacing another element, so your zinc is now ends up being zinc chloride, and your hydrogen is released as your element. So that's also a redox reaction. That's a displacement or single replacement reaction. How about this one? You don't see any elemental substance there, right? So you can't tell right away. You're going to have to go into the more general method of determining whether it's a redox reaction or not. So it's a question mark at this point. The last one, that's a combustion reaction that involves an elemental substance, O2. So you know that that is a redox reaction. So even though you couldn't tell at this point, at least at this point in the lesson, that choice D is a redox reaction. That's the only choice you have left, so that has to be the answer. In fact, this reaction is not a redox reaction. Okay, precipitation reactions in general are not redox reactions. This is an example of a what you would call what a double replacement, where you imagine you have exchanging of partners here. So this gives you a precipitate of barium sulfate, and it's also an acid-base neutralization. Your H plus from your sulfuric acid and your hydroxide from the barium hydroxide gives you water. So this is a reaction that's at the same time precipitation and acid-base neutralization. Those types of reaction you'll find are generally not redox reactions. Okay, they're not redox reactions. So correct answer is D. Look for an elemental substance so you can tell right away. All right, let's try another one. Which of the following is a redox reaction? A, B, C, or D? Okay, let's see. Fell for my trick. All right. This is an elemental substance. That's an elemental substance. So definitely that's a redox reaction. Okay. In fact, your silver, in pure silver, it has a charge of 0, right? Whereas in silver chloride, you know that has a charge of +1. So what happened to the silver here? It lost an electron. So we say the silver was oxidized, right? Silver atoms were oxidized to silver ions, and then your chlorine here, the atoms in your chlorine got reduced to chloride ions. So that involves a gain of 2 electrons. Reduction. So that's redox. But what about choice A? That's not a pure elemental substance. The fact that it is written with a charge on it, that's an ion. That must be part of something. Ions don't come by themselves. So that's not a pure elemental substance. That is a part that must have come from some compound. This is if you have to remember that your previous lessons on net ionic equations. This is an example of a net ionic equation. It involves some other things, but they were canceled out because they turned out to be spectator ions. Okay. Chloride here is not a pure elemental substance. But how do we know that this is not a redox reaction? Well, Ag plus chloride gives you AgCl. What do we know about silver and silver chloride? It has a charge of +1, and the chlorine in silver chloride has a charge of -1. Nothing happened to the silver. It's still +1. Nothing happened to the chloride. It's still -1. They just happen to have come together to form a precipitate. This is a precipitation reaction. Okay? You have 2 ions in aqueous solution combining to form a precipitate. Okay? It's not a redox reaction. So the correct answer is just B. Sorry. All right. Let's take a look at. I'm gonna give you another one. Let me try another question similar to that one. Make sure you got it. Okay, which one of this is a redox reaction? Let's see. Calcium plus 2 fluorides gives you CaF2. And the other one would be calcium plus F2 gives you CaF2. Okay? Which A or B, which one is a redox reaction? Very good, much better. Okay? Calcium here has a charge of +2. You know that calcium, when it forms compounds, if you find it in nature, as part of compounds, belongs to group 2A. They always have a charge of +2, right? But calcium in the pure element has a charge of 0. So what happened to the calcium? Did it get oxidized or reduced? To go from 0 to a positively charged particle, would it have to lose or gain electrons? Gain or lose? Lose electrons, right? You lose 2 electrons, you become positively charged. If you're losing negatives, you become positive. Okay? So discard your negative feelings, you're oxidizing yourself. Okay? Again, you become positively charged. So lose 2 electrons here, so that's an oxidation. So you can see those are elemental substances, calcium and F2. Whereas here, calcium is +2. Over here, calcium is also +2. This particular calcium ion must have come from some compound, and what you have here is what you would just call the net ionic equation. Okay. So let's move on then. We said that something like a combustion of carbon, for example, with to give you carbon dioxide. Okay, that involves 2 elemental substances, so that's a redox reaction, right? But how can there be electron transfer there? Carbon dioxide it's not an ionic compound. Here's your Lewis structure for carbon dioxide. The carbon and the oxygen are sharing electrons. There is no electron transfer, it seems, right? But you have to realize that, okay, even though the carbon and the oxygen are sharing atoms, in general, sharing electrons, in general, sharing of electrons is not equal. We've learned earlier that this is a polar bond. This bond is polarized towards oxygen. Electrons actually spend more time with the oxygen than they do with the carbon. Similarly, this bond right here, carbon to oxygen, is also polarized towards the oxygen. Oops, I just took a poll. Oh. Let me go ahead and press A for that one. That's a bonus. Thank you. All right. So we also say that, and let me mark that as correct. All right. So we also say that this bond right here is polarized towards oxygen. Okay. So in a way, even though the electrons are shared, there is some partial transfer of electrons to the oxygen from the carbon. Okay. So in that sense, we say that you can think of oxygen atoms as having gained electrons and the carbon as having lost electrons in the process of burning carbon to give you carbon dioxide. Okay, so that's why that reaction is also considered a redox reaction. Now, we don't like to have to deal with partial charges. Okay, and so as a matter of convenience, we define the thing called oxidation number. Okay. To allow us to determine if a reaction is a redox reaction, okay, without having to worry about partial charges. And in general, what we do is we examine our reaction and we look at the oxidation numbers. And if we see that a particular atom has gained oxidation, has an increase in oxidation number, then we say it's oxidized. And when you see a decrease in oxidation number, then it must be reduced. Okay, so this one, increase in oxidation number is oxidation, decrease in oxidation number is reduction. Okay, so what's an oxidation number then? Well, if you're dealing with a single atom or a monatomic ion, a monatomic species, the atomic number and the oxidation number is just the charge. So for example, what would be the oxidation number of a magnesium atom? What's the charge of a magnesium atom? Neutral, so the charge is 0. So oxidation number of a magnesium atom is its charge. What's the oxidation number of chlorine in magnesium chloride? Well, what do you know about magnesium chloride? It's made up of magnesium ions and chloride ions, right? For every magnesium ions, you see 2 chloride ions. So given that, what's the oxidation number of chlorine in magnesium chloride? Each chlorine atom in MgCl2 is actually in what form? In the form of chloride, right? So the oxidation number of Cl, or chlorine, in MgCl2 is -1. Okay, there's two of them, but each chlorine has a, we say, has a charge of -1. So each chlorine in magnesium chloride has an oxidation number of -1. What's the oxidation number of magnesium in MgCl2? +2. Yes, the total is 0. The total is 0 because you have a +2 and two -1s. That's a total of 0. Okay? Now, so that's if you're dealing with monatomic species. Okay? And you have to realize that you can have a monatomic ion within a compound. Right. Now, what if you have a molecule or a polyatomic ion? Then the atoms there do not have a charge. Okay? A charge, the whole thing, the molecule has a charge of 0. A polyatomic ion has an overall charge. But the individual atoms within that structure do not have a charge. Okay? So in order for us to be able to keep track of electrons, we have defined the oxidation number as a fictitious charge that we assign to an atom. So this is similar to what you've learned when you talk about molecular structure, when we were dealing with molecular structure. This is similar to what we call the formal charge. Except in the formal charge, when determining formal charges, we assign equal ownership to the shared electrons to the atoms that are sharing them. Okay? But when you're determining oxidation numbers, you assign ownership of the shared electrons to the more electronegative atom. So let's illustrate that with carbon dioxide. Okay? If you were to draw carbon dioxide, the Lewis structure looks like this. All right? So, if you recall, how many valence electrons does an oxygen atom have if it were by itself? Where would you find oxygen in your periodic table? Oops. Where would you find it in your periodic table, huh? Group 6, right? Group 6A, column 16. Okay? So that means it will have a neutral oxygen atom, if you recall, as an electron configuration of 1s2, 2s2, 2p4, right? It has 6 valence electrons. Okay? By itself, if it were alone, an oxygen atom would have 6 valence electrons. Now, in this structure, okay, remember a Lewis structure shows you how the valence electrons are distributed among the atoms. In this structure, the oxygen owns how many? 2 plus 2 plus 2 plus 2. It's surrounded by an octet, right? So it appears to own 8. Okay? We say it appears to own 8 because we're going to make the assumption, for purposes of calculating oxidation number, you assign ownership of shared electrons to the more electronegative atom. So we're going to say that even though this double bond right here is shared between carbon and oxygen, it actually, we're going to assign ownership of that to oxygen. So we're going to say it belongs to oxygen. So from 6 in a neutral atom to 8 in the structure as drawn here, it appears to have gained 2 electrons. So we say it has an oxidation number of -2. So in this structure, in carbon dioxide, this oxygen atom appears to have gained 2 electrons for purposes of calculating oxidation number. And this oxygen atom right here also appears to have gained 2 electrons, so its oxidation number is -2. So we are assigning a fictitious charge to it. It's not really -2, the actual charge, right? But we don't have to worry about partial charges. So we're just going to say, oh, let's just give him the whole thing just for counting purposes. Okay, and then carbon right here, we say, appears to have lost how much? 4. Okay, carbon, if you look at your periodic table, is in group 4A, right? The column number where your atom belongs tells you, this is a review, tells you how many valence electrons a neutral atom would have. The lowest symbol for carbon atom would have 4 dots, remember? Oxygen would have 6 dots. Okay, the 2s2, 2p4 would give you 6 electrons. Okay, so in carbon dioxide we say, okay, that the oxidation state of oxygen, each of the oxygen atoms has an oxidation state of -2. They don't have a charge of -2. Their oxidation state is -2, or their oxidation number is -2. Carbon, we say, has an oxidation number of +4. That +4, that's not the charge of carbon. That's a fictitious charge we're assigning to carbon for purposes of keeping track of electrons. So that's called the oxidation state of carbon. Okay? What about peroxide? Another example here. What's the lowest structure for peroxide? Have a single bond between the two oxygen, and then you have how many valence electrons do we need to distribute for that? Each oxygen has how many valence electrons? It belongs to group 6A. It has 6 valence electrons times 2. That gives you 12, right? And then you have a -2 charge. That means 2 more electrons. That's a total of 14 electrons. And so the way you draw the lowest structure, this is valence electrons, okay? You draw the lowest structure for peroxide. You draw a single bond, do an octet around each oxygen, and that takes care of 14 valence electrons. There's 6 here, 6 here, 6 lone pairs on each oxygen, and there's 2 in the single bond between them. That's a total of 14. So the lowest structure for peroxide is O2 with a -2 charge. So put this in brackets and put a -2 on the outside. Okay, so that's the lowest structure for peroxide. So based on this lowest structure, what is the oxidation number of oxygen? Well, which one's more electronegative, oxygen or oxygen? Neither one, right? So we cannot assign ownership of these 2 electrons in between to either one, right? They have to be split 50-50. So if they split 50-50, how many electrons does this oxygen appear to own? 7. And how many does this appear to own? 7 valence electrons. Normally an oxygen atom would have how many? So this one appears to have gained 1, right? So 7 minus 6 minus 7 would be -1. So we say the oxidation number of this oxygen is -1. The oxidation number of this other oxygen is also -1. It's as if each oxygen gained 1 electron. So we say the oxidation number is -1. They don't have a charge of -1. The pair as a whole has a charge of -2. Okay? But it's as if each one has a charge of -1. Okay, what do you think the oxidation number of mercury is going to be in Hg2 plus 2? That's the mercury 1 ion. Let's make that a clicker question. Is it 1 or B, is it 2? Plus 1 or plus 2? For each mercury in the mercury 1 ion, or mercurous, this is called mercurous ion, or mercury Roman numeral 1. What is the oxidation number of mercury? Is it plus 1 or plus 2? Okay, correct answer is plus 1. Okay, the pair as a whole, okay, they're sharing electrons. The pair as a whole has a charge of plus 2. Since we can't expect either one of them to own the shared electrons, we have to split electrons 50-50. We expect both of them to have the same oxidation number, right? So since the overall charge is plus 2, it's as if each one has a charge of plus 1. So we say the oxidation state is plus 1. They don't have a charge of plus 1. They have an oxidation state or oxidation number of plus 1. And that's why, that's really what that numeral, Roman numeral means. It's not really the charge. When you attach it to the name for a transition metal, that's actually oxidation number. So when I say mercury 2, okay, Roman numeral 2, we said that that's mercury with a plus 2. Okay, that 2, in this particular case, just happens to be this, it just happens to be that plus 2 is also the charge and the oxidation number. Okay, but that Roman numeral 2 actually refers to the oxidation number. Okay, so in fact, sometimes you would write for something like maybe SO2, for example. Okay, the oxidation number of sulfur here is plus 4. Okay, we'll learn how to do that in a short while. And sometimes you call this sulfur Roman numeral 4 oxide. Okay, that's one way it could be called. Okay, you probably learned earlier that what do you call this? Sulfur dioxide, right? So this is another way that could actually be called. You specify, so when you say Roman numeral 4 there, you're specifying the oxidation number. Sulfur certainly doesn't have a charge of plus 4 here. Okay, its oxidation number is plus 4. All right, let's take a look at this one. Which of these structures has carbon atom with the highest oxidation number? Right, you just take a wild guess. Here's ethanol. So you can figure, let me help you figure out the oxidation number of this first carbon right here. Which one's more electronegative, carbon or hydrogen? Carbon. One mnemonic that I made up for myself to remember the sequence of electronegativity is FONCLBRISCH, at least the common nonmetals. So I just remind myself of this. I try to pronounce it, make up a word or phrase from it. Phone call brish. Okay. So hydrogen is less electronegative than carbon. This is 2.2 or 2.1 depending on what you're looking at, which textbook you're looking at. I think let me see. Pauling's original number was 2.2, but in 1961 he changed that to 2.1. And fluorine, of course, is 4.0 on that scale, right? So those are the most electronegative atoms. So carbon is more electronegative than hydrogen. So according to this sketch right here, okay, how many electrons belong to this carbon atom right here? It owns all of these 6, right? Why? Because it's more electronegative than hydrogen, and it owns half of this pair because carbon and carbon, you have the same electronegativity. So this carbon right here appears to own 7, right? Now a normal neutral carbon atom by itself would have how many valence electrons? 4 valence electrons. It belongs to group 4A, right? 1s2, 2s2, 2p2. In the valence shell, there's 4 valence electrons. 4 electrons. So 4 minus 7. So this carbon appears to have gained 3 electrons. So we say the oxidation number of this carbon is -3. Okay? Can you quickly tell me what's the oxidation number of this carbon right here? It's -3, just like the other one. How about this carbon right here? Also -3. Let's try this carbon right here. The second carbon. Okay. Does it own these 2? Yes. How about these 2? Yes. How about this? Half of it, right? So 1 of that. What about these 2 right here with the oxygen? It doesn't own that. Oxygen is more electronegative than carbon, right? So that doesn't belong to carbon. So this middle carbon right here, or this second carbon, how many does it appear to own then? 2, 4, 5, right? So 4 by itself, on its own, -5, it appears to have gained 1 electron. So the oxidation number of carbon here is -1. Okay? So let's take a look at the other two. And so which of these structures has a carbon with the highest oxidation number? Is it A, B, or C? Think about it or try to figure it out. You just need to compare figure out the last two, right? This one right here and this one right here. Let's see how we're doing. Okay, all over the place. Let's see. What's the oxidation number? Oops. Of this carbon right here. What would it be? How many does it own? It owns those and those. That's 4. Does it own any of this shared with oxygen? It doesn't own any of those, right? So these, huh? Oh, that's right. Only one of those, correct. Very good. So it owns that, and it owns one of these two. So that's 3, right? So 4 minus 3, oxidation number is +1. Okay? How about this carbon right here? This one now belongs to oxygen. These two pairs belong to the oxygen, so it only owns half of that pair. So here it only owns 1, right? So 4 minus 1, it now has an oxidation number of +3. It appears to have lost 3 electrons. Here it appears to have lost 1 electron, and here it appears to have gained 1 electron in comparison to the neutral atom. So correct answer is C. Okay? Now, take a look at this. This is actually what happens to wine when it sours. Ethanol, that's what gives you the hangover when you drink wine, right? CH3CH2OH. When it turns sour upon exposure to air, okay, we say it is oxidized to acetic acid. Sour taste, same sour taste in vinegar. Okay, so that's acetic acid. So from what was the oxidation number here? -1 to +3. An increase in oxidation number is oxidation. Okay, this happens when this reacts with oxygen. Another way of looking at it is you're bonding your carbon to more oxygen. See, this is just bonded to 1 oxygen here. Okay, it's sharing with oxygen. Here there's more sharing with oxygen. The more an atom shares with oxygen, unless it's fluorine, which is more electronegative than oxygen. In general, oxygen is the second most electronegative element, right? The more an atom shares with oxygen, we can say that the more it's losing electrons. So combining with oxygen means losing electrons, so that's getting oxidized. In fact, the original meaning of oxidation is reacting with oxygen, but it's now been generalized, the process where you're losing electrons. Because in general, when an atom combines with oxygen, it loses, in a way, it loses electrons to the oxygen. So if you look at structures like this, you can just look at, if you're going from an alcohol here in ethanol to acetic acid, which is an example of what's called a carboxylic acid. If you have more bonding of the carbon to oxygen, that's an oxidation reaction, half reaction, okay? So what are the rules for assigning oxidation numbers? If you're dealing with an elemental substance, there's no reason why electrons would belong to one element. If you have any shared electrons, there's no reason why it would belong to one atom versus another, or they're all the same. So for an elemental substance, the oxidation number for all the atoms is 0. If you're dealing with compounds, okay, if the compound has monatomic ions, the oxidation number is just the charge. If it's made up of molecules, or it has polyatomic ions, okay, then the rule is find the most electronegative atom and then assign it a negative oxidation number, as if that particular atom is isoelectronic with the closest noble gas. So if you see a fluorine there, give it a -1. Fluorine is the most electronegative atom, right? So anytime you find fluorine in a compound, automatic, -1 oxidation number. Oxygen is usually -2 because that's the second most electronegative element. Oxygen gains 2 more electrons, becomes isoelectronic with a noble gas. Anytime oxygen bonds with another atom, it owns that shared electrons. So it ends up having 8, so 6 minus 8, 6 by itself, 8 in a noble gas-like configuration. Oxygen will have an oxidation number of -2. What's one exception? If it's combining with fluorine, right? Oxygen versus fluorine, fluorine wins. So OF2, for example, okay? What's the oxidation number of oxygen in OF2? Each fluorine is going to have an oxidation number of -1. Then the oxygen must have an oxidation number of +2. Okay, it's an important rule that oxidation numbers in a molecule or a polyatomic ion, they must all add up to the overall charge. So if you're dealing with a neutral molecule, all the oxidation numbers must add up to 0. Okay, halogens. What are the halogens? That's fluorine, chlorine, bromine, iodine. Okay, they're usually -1. They're among the most electronegative atoms. Okay, so you have to remember your electronegativities. You have to more or less know the sequence. All right, so let's apply that to this reaction. This is a redox reaction, okay? So what's reduced in this reaction? Which atom, which element? So you assign oxidation numbers. This is an elemental substance. What's the oxidation number of copper then? According to our rule, 0. Pure elemental substance, 0. How about HNO3? All right, HNO. Oxygen is usually what? -2, right? So -2 times 3, that's -6. Oh, I forgot something about hydrogen. Hydrogen, okay, it's usually +1 if it's among nonmetals, if it's sharing electrons with nonmetals. You'll notice hydrogen is one. Among the nonmetals, hydrogen is the least electronegative, okay? But if it's combining with a metal, for example, in the AlH4, aluminum hydride ion, okay, it's bonded to an aluminum atom, okay, and the overall charge is negative, then the hydrogen has a -1 formal charge. Why? Hydrogen, to be isoelectronic with the nearest noble gas, just needs 1 more electron, right? So you need 1 more electron to add to that to make it helium-like. So hydride has a -1 oxidation number. Okay. So hydrogen in this case is 1 +1. So what's our nitrogen then? Well, let's call that X. This whole thing should add up to what? That should not be, that's not +1, that's not +6. It's +1 for the hydrogen, plus X for the nitrogen, plus -6 for the 3 oxygens. Together, they should add up to 0, right? So what's the oxidation number of nitrogen? +5. Okay, so the oxidation numbers here are +1. Let me do this. Hydrogen is +1. Nitrogen is +5, oxygen is -2. What about NO? Oxygen What is it? Second most electronegative. We don't have a fluorine there, so oxygen here must be -2. So the nitrogen here must be +2. Okay, oxidation numbers must add up to 0 for a molecule. How about copper nitrate here? We've already done the nitrate, so it's the same thing here. Nitrate. Okay, let's look at nitrate. Okay, each oxygen is how much? Oxidation number of -2 times 3, that's -6. So the nitrogen must be what? X plus -6 must be equal to -1. That's the overall charge. So what's the nitrogen here? +5. So if your polyatomic ion remains more or less intact during the reaction, then the oxidation number hasn't changed. So nitrogen here is still going to be +5. Each of the oxygen here will have an oxidation number of -2. So what's the oxidation number of copper here? How do you figure it out? You have copper combined with 2 nitrates. Each nitrate, remember, has a -1 charge. So what must be the charge of copper? Must be +2. Okay, so this copper right here is +2. And then finally water. What's oxidation number of oxygen here? -1. What's the oxidation number of hydrogen then? I'm sorry, -2 for oxygen. Hydrogen must be +1. When we say oxidation number, we do it on a per atom basis. Okay, so there's 2 hydrogens there. So the 2 hydrogens together is +2, so the hydrogen must be +1. Okay, given these oxidation numbers, remember what did we say about oxidation and reduction? Increase oxidation number, we say that element or that atom is oxidized. If the oxidation number goes down, we say it's reduced. So what is reduced in this reaction? Is it copper, hydrogen, nitrogen, or oxygen? Some more answers? A bit more clicks. So correct answer is, what's reduced? The nitrogen went from +5 here, okay, to +2 over here. So you say HNO3, okay, the nitrogen in HNO3 got reduced to NO. So that's reduction. Okay? The species that's involved in the reduction is HNO3, and the product of the reduction is NO. Now you might say, the nitrogen here is still +5. Then that tells you there must be some extra HNO3s where the nitrates did not get reduced, where the nitrogen did not get reduced. But this is the only source of nitrogen, so whatever gave you NO must have been an HNO3. Okay? So nitrogen, we say, is reduced. Correct answer is C. What is oxidized here? Your copper goes from 0 to +2. So you say copper went from 0 to +2. Okay? So, okay, you say copper nitrate. That would be oxidation. So your nitrogen went from a +5 oxidation state in HNO3 to a +2 in NO. That's reduction. Copper went from a 0 in copper metal to a +2 in copper nitrate. That's oxidation. Okay. Right. So how do you balance redox reactions? Most redox reactions, a lot of redox reactions are not straightforward as far as balancing is concerned because they might involve a lot of reactants and products. If you have a simple redox reaction, you can probably just balance by trial and error. But if you have a reaction like this, okay, chances are you're going to have a hard time balancing it by just trial and error. Now, it helps a little bit if you do a little algebra to balance it, but it's almost a necessity. It's pretty much a necessity that you take into account electrons lost and electrons gained when balancing a redox reaction. That helps a lot in figuring it out, especially if you're going to do it by trial and error. Okay, so in a balanced redox reaction, you have to realize that if something gets oxidized, something else must get reduced. Okay? If something loses electrons, those electrons go somewhere else. So if something loses electrons, those electrons are gained by something else. So if something is oxidized, something else gets reduced. What did we say got reduced here? Your nitrogen went from a +5 to what? A +2, right? So that's how much? A change of 3, that means gain or loss of electrons. This is reduction, right? Reduction, do you gain electrons or lose electrons? Gain electrons. Gain of how many electrons? 3 electrons per nitrogen, right? And what happened to your copper? Remember what did happen to our copper? From 0 to +2, right? That's oxidation. So when you become more positive, that means you've lost electrons. How many electrons here lost? 2 electrons for every copper. All right, so since electrons lost must be equal to electrons gained, what that tells us is every time we get one of these, we're gaining 3 electrons. We have to be losing 2 electrons somewhere, 3 electrons somewhere also, but this one only gives you 2 electrons. What should we do to balance electrons lost and gain? We adjust coefficients, right? So we find the least common multiple of 3 and 2. What's the least common multiple of 3 and 2? 6. How can I make 3 equal what do I multiply 3 with to get 6? 2. So what I need to do is this has to happen, okay? This thing has to happen 2 times, and every time this thing happens, reduction happens twice, my oxidation must happen 3 times in order to balance electrons lost and gained. So what that means is if my coefficient for this is 2, then my coefficient for this other one must be 3. So that ratio must be maintained 2:3. So if I were to end up balancing this equation with a 4 over here, what would my coefficient over here be? It would have to be a 6. 4:6 is the same thing as 2:3. If I went back and forth, tried to balance this equation, I ended up with an 8 over here, what would this have to be? This would have to be a 12. Okay? 2:3, 4:6, 8:12. Okay? So that sort of fixes that. That constraint fixes those two and simplifies things for you. You have less to worry about in terms of trying to adjust coefficients. Okay? Now, as far as balancing the rest of this equation, you should already know how to do that. So I'm just going to leave it at that. Okay? Try to balance this on your own. Okay? But the important thing to realize is these other coefficients you can change, okay? But this too must be on a 2:3 ratio. Or do you need me to go through this process just for illustration? Or can you do it on your own? Okay. All right, so that has to be a 2:3. one thing I like to do instead of going back and forth using trial and error is I use algebra. So I just assign a letter here. I'm going to call this A, B, 2, 3. I'm just going to fix that at 2 and 3. Okay? And then, so the other coefficient is C. Okay? So I can balance my equation like this. So I'm going to represent my unknown coefficients by letters. So what do I know? If I were to balance copper, how many coppers do I have on the left? A times 1, right? How many coppers do I have on the right? 3. This is the only place I find copper, 3 times 1. If I were to balance H, what would I have on the left? How many H's do I have on the left? B times 1. How many H's do I have on the right? 2C. Right? How about nitrogen? How do I balance nitrogen? How many nitrogens do I have on the left? B, right? How many nitrogens do I have on the right? There's 2 times 1 there, plus how many nitrogens here? 3 times 2, that's 6, right? And finally, if I want to balance oxygen, what should I have? B times 3, so that's 3B. How many oxygens do I have on the right? There's oxygens here, so that's 2, plus oxygens here is how many? 2 times 3, that's 6, times 3, plus 6 times 3, 18, plus another oxygen here, C, right? Do I know what A is? A is 3. Okay. What else do I know? Do I know what B is? It's 8. Do I know what C is? I know what B is, so C is B over 2, right? So what's B over 2? 4. Correct? Alright, so let's try that. Let's verify. I have 3 coppers plus 8 HNO3 gives me 2NO plus 3 CuNO3 2 plus 4 H2O. Let's see if it's balanced. How many coppers do you have on the left? 3. 3 on the right. Hydrogens? 8. 4 times 2, 8 on the right. Nitrogens? 8 on the left. Okay, how many do I have on the right? 2 here, and then 3 times 2, 6 there. That's 8. Okay. Oxygens, how many on the left? 8 times 3 is 24. On the right, I have 2 plus 18 plus 4. That's 24. So this equation is balanced. Okay. See how easy it is if you do things using algebra? Otherwise, you'll be going back and forth, back and forth.
That's the only way they taught us.
Huh?
That's the only way I was taught was to
going back and forth, trial and error.
And I was like, next question.
So this is actually very easy to balance. All right. Now, the ion electron method. This might be a good time to pause, huh? Let's continue this next time.